Hey there, welcome back to the fourth episode. I've got a shorter one for you today because I needed to cover a few more basic concepts before we tackle the meat of this unit, so I just bit the bullet to make it its own episode, but I digress. We're going to cover graded potentials and IV plots today, so by the end of the video you should be able to answer the questions, what is a graded potential, and how do we plot currents and voltages? Remember that membrane potentials are the electrical driving forces in the neurons. Using these, two types of currents are generated, the all or nothing spike of the action potential versus the gradual slope of the graded potentials. When neurons fire, action potentials are generated, but the postsynaptic neuron can respond to the pattern of fire with graded potentials. This has implications in combining information from many different input neurons and is used primarily to transduce sensory and synaptic input from one cell to the next. We can combine many graded potentials to bring the postsynaptic neuron from rest up to threshold, allowing it to fire an action potential, propagating signals from cell to cell. To explain how these graded potentials work, I'm going to introduce another equation. I ion equals G ion times the difference between Vm and E ion. This equation relates the current or ion flow of a single ion to the conductance and ionic driving force. Conductance is, as the name suggests, a measure of how conductive a membrane is, and can be modulated by opening and closing ion channels. The driving force calculates for how different the membrane potential is from the equilibrium potential. It's called the driving force because it shows the difference between where the cell is versus where it would need to be for the ion of interest to be at equilibrium. The larger this is, the more of a driving force there needs to be to get to equilibrium. Cells can generate the graded potential by modulating our conductance though. Opening up ion channels increases conductance, enabling more ion flow, while closing them drops conductance, cutting off ion flow. Remember, the membrane potential is a combination of several equilibrium potentials, so we're shifting some of those levers to weigh ions more or less in the overall sum. Gating is key to make sure the right amounts of ion channels are open or closed. Alright, time for a quiz. Assuming the same conductance among all ions, which of the following has the greatest magnitude for current for a membrane at rest? As a hint, I've given the equation you'll need to know in the question itself. A is a sodium ion with plus 62 millivolts as its E ion. B is a potassium ion with an E ion of minus 80 millivolts. C is a chloride ion with an E ion of minus 65 millivolts. And D says all three will have the same magnitude. The answer here is A. It can be tempting to pick B because potassium has the highest E ion just by straight magnitude numbers, but let's look at the equation once more. We're assuming two things. Conductance is the same among all ions and that the membrane is at rest. So G ion among all of these is the same arbitrary number, which wouldn't exactly model real life, but for the purpose of this question makes our calculations easier, so we'll let it rock. This means that we can plug in the resting potential value of minus 65 millivolts into that Vm term in the equation, because that's our membrane potential at rest, and then we can calculate our other choices. This gives Na with the highest value for our current, which means the answer is A. We can graph how the ions around the membrane would move in relation to current and voltage using a current voltage plot, also known as an IV plot. These values can be kind of confusing, so let's slowly consider what it means. A positive value means a positive current at a given membrane voltage. This corresponds to the outside of the cell becoming more positive relative to the inside. This means we are hyperpolarizing the membrane, and either cations are effluxing, leaving the cell, or anions are influxing, entering the cell. On the flip side, where there is a negative Y value on the IV plot, you're going to see cation influx or anion efflux. Where the graph crosses the x-axis is the reversal potential, where the direction of ion flow would turn around. So at reversal potential, there wouldn't be any net movement or inside or outside, zero current. This corresponds to our equilibrium potential. So the x-intercept on the plot can be an experimental way to see E ion. Ready for the next quiz question? The current value on an IV plot is negative. Which of the following ion flows can explain the observed value? A. Sodium is entering the cell. B. Sodium is leaving the cell. C. Chloride is entering the cell. And D. Oxygen is leaving the cell. I'll give you some time. The answer here is A again. We can immediately discard answer choice D because oxygen is not a relevant ion for us here. We have a negative current, so either cations are entering the cell or anions are leaving. This allows us to eliminate choices B and C because sodium cation and chloride anion would be going the opposite direction as what is in the answer choices. Therefore, A is the correct answer. Well, that's all I had for this one. Today, I introduced the concept of graded potential, the counterpart to the all or nothing Asher potential. We also got to see how we can study how ion currents interact with the membrane voltage, as well as how to look at and interpret IV plots. Next time, I'm going to talk about synaptic transmission and wrap up the first half of this unit. Timestamps and extra info are in the description as always. Thank you for watching, and I hope to see you next time.